So let's talk about power series. Okay. What is a power series? The power series is a function from R to R. But if you take other courses, you can also take this to be a complex. So complex. Yeah, and it's defined as this guy here. Okay, that's a power series. Right. So recall, is it here? Anyways, so recall. So an example that we had. So let me find it in my notes. So, right. So we had the power series for arctan. So arctan of x, we found it to be equal to summation from n to 0 to infinity 2n plus 1 of x 2n plus 1. But this was only for, let me make it clear, only for x in minus 1, 1. Okay. I guess let me try to convince you, because for example, for x equal to, I don't know, 2, what do you get? Minus 1 to the n, 2n plus 1. You get, yeah, fine, let me write it like this, 4n, and then let me bring out the 2. So you get this guy, this series, which diverges. Let me show you why. Because, for example, the limit is not 0, because an equal to I can do it like this, just to drive the point. It goes to plus infinity. Exponential always beats polynomial. Right? And for a series to converge, you so recall an is finite if and only if. So if you have this, you get that an goes to 0. So conversely, an not 0 implies summation an dne doesn't exist. Okay. Okay. Yeah. Now let's see. I did it for 2, but you can do it more carefully. Let's look at x equal to 1 plus epsilon for any epsilon positive, well, then again, you're in trouble. An is equal to 1 plus epsilon to the n, 2n plus 1, and again, it goes to plus infinity. Okay. So we call r equal to 1 the radius of convergence for the series, for the power series what was it? Minus 1 to the n, 2n plus 1, x to the 2n plus 1. Okay? So, meaning that only within this interval can you talk about, so yeah, what was the graph of arctan? Let me draw it. At 0, you're 0, right? So, something like this. So only within here can you approximate by power series. Outside, you cannot. No power series. Yeah. Okay. Happy? So right, yeah, more generally, the definition is for power series summation ak xk for power series ak xk the if for all x in in open minus RR, the series converges. And R is maximal, so there is no maximal, and R is maximal, i.e. For R plus epsilon, the series doesn't exist. We call R the radius of convergence. All right. I think we got it. Okay, fine. All right, so now let's prove a theorem to actually get this R. So this is called Hadamard's theorem. We get the statement, right? For the power series summation an xn, let we call it alpha to be the lim sup. So we will define all these things in a second. Of an and then 1 over n. Then the radius of convergence is equal to, so the radius is equal to 1 over alpha. Okay. You can find the radius. Is it possible to have multiple radius of convergence when the series converges in various disjoint domains? So, I don't have an example in mind, but yes, there are cases. Yeah, but let me. That's a good question, but no, here we will always have unique, and like in fact we have it here defined. So no, in the reals, the radius is unique, but they are, but in complex, I remember, but in the complex domain, things can be more complicated. So can be complicated. In complex, it might not even be a disk. It might be some complicated domain. So there is no, it's not, there's not even a notion of radius. But yeah, so. But Ajit, yeah, if you have a concrete example, let me know and we can talk about it. It's very interesting. Okay. Right, so let's prove this. Right, okay, so again, recall it's called the root test. What is it? Consider for sequence of real numbers for series. I don't know. When you write Bn, it exists, converges. It converges. If the lim sup of Bn n to the square root over 1 over n is less than 1. Okay. If it's equal to 1, it's indeterminate. It might or it might not converge. And bigger than 1 diverges, DNE. Okay. All right. All right. So we have that. So let Bn equal an x to the n. And right, so we get lim sup lim sup of an xn to the 1 over n. And we ask this to be less than 1. So we ask this. But here you see there's a nice cancellation. an x less than 1. And yeah, we call this guy alpha. So we get x is strictly less than 1 over alpha. Okay. Right. What do I want? Yeah, so that's why. So yeah, indeed, we let R to be a 1 over alpha. Now let's prove that in fact you have uniform convergence. Now we prove that we have uniform convergence for all x in a compact subinterval within the radius of convergence. Okay. So in other words, R is less than big R. Okay. So we will use the M-test. So we will use the M-test. What do we have? We have that sup x in minus RR of the coefficient, so it's an x to the n, is less than, an r to the n, right? And okay, and by the root test, we got that lim sup. We get that, yeah, so an, rn, 1 over n. How do you say it? So again, this is alpha times r, and this guy is less than capital R, which is 1, right? So this guy is less than 1, strictly less than 1, right? So yeah, to be clear, here we mean sharp, so strictly less. Yeah, so that implies that summation of an r to the n exists, converges. Okay. So these were the two conditions for the M-test. So by M-test, summation of an xn converges uniformly. Converges uniformly for all x. So for all x in minus RR. Okay with everyone? Okay, so all right. So Hadamard's theorem tells you that, yeah, that that this guy converges uniformly. If you take for all compact intervals. Okay. we should do some examples. So let's see. Oh yeah, one quick corollary. So finding this lim sup can be hard. Corollary. You know, if the ratio limit exists, so meaning limit, what did I say? Limit of an plus 1 and an, if that guy exists, then in fact that would be your radius. Then you know, then alpha is equal to that, and so the radius can also be written as you know, an plus 1. Okay, that might be easier to work with. Oh, we have to do some examples. Right, so example. So this is pretty easy. Consider the power series for the exponential. And we ask, what is its radius of convergence? All right, let's see. Meaning that you have uniform convergence uniform. So we did this from the previous class. So we already found you know, we already found that R was infinity. But let's do it here using Hadamard. Okay, so right, so we have 1 over R is equal to alpha, which is the lim sup of what is it? Xn n factorial to the 1 over n. Right, so you get no. I'm sorry. Yeah, I just meant this guy. So this is lim sup of 1 over n factorial to the 1 over n. Okay. So hopefully you've seen this before. This is called Stirling's formula. Actually, I want to give you the precise asymptotic. I was going to give you a rough one, but I want to give you the precise. Okay. So let me write it carefully. So n factorial, what was it? Yeah. So this is by Stirling's formula. Okay. So that means that you get lim sup of what? Yeah, the point is you can ignore all the other guys and you're just left with 1 over n. And so you get 0. So that tells you that 1 over r is 0, which tells you that r is plus infinity. Okay with everyone? Are you sure? You can just tell me. We don't have to go really fast. But I understand that this root test can be a bit hard to work with. So you can also use the ratio test. So, you know, this is, what do you call it? You know, you get an plus 1 and an. And that's much easier to work with. So you have n factorial and n plus 1 factorial. And if you remember the definition for factorial, you're just left with n plus 1. And again, you get 0. So you get r is plus infinity. Okay. Can you explain the Stirling part? Yeah. So I'm not going to prove this. That requires a little bit of machinery. Is that what you're asking, or? So this is you can use it without proof, because the proof goes beyond this course. It uses the central limit theorem. And if your question is how we go from here to here, so let me do it on the side. So plug everything in. What do we have? We have 2 pi n over e to the n, and then 1 over n. Okay. Let's split this up. 2 pi n, 2n, n, and 1 over e. Right. So this guy, you can show that it goes to 1. Right, okay, so we have an e here. And but it doesn't matter, so it goes to 0. Is that okay? All right. Why did we need to show uniform convergence for Hadamard's? Okay, so I didn't write the full statement. Let me just say, right. No, it's a good question. Where is it? So this is the rate of convergence, and then, I mean, how do you say it? No, Trevor is right. I should have made this more clear. Where is it? Here. So the series converges uniformly. I should have added that. So by radius of convergence, we mean the places where the series converges uniformly. Trevor? Yeah, okay. So Hadamard gives you a very strong statement that, yeah, you have uniform convergence. Radius of uniform, let me add it. I know it's not in the book, but I want to make it clear. So we mean radius of uniform convergence. Thank you, Trevor. Okay, what's next? Oh yeah, we have to talk about the endpoints. Yeah, that's important. So Hadamard's theorem, doesn't give information. Doesn't give information on the endpoints. On the endpoints x equal to plus minus r. So let's do some examples to see that you have D and E. Okay, so what's the example? Yeah, let's do that one first. I want to show you why you can have D and E. Actually, let me do an easy one first. Yeah. This is one where you have convergence. So here you will have it. Consider, and I think this is in your book too. What is it? 2 to the 2n, then n to the 2 xn. Let me make it n. Yeah. Okay, I like that. Let me make it n. All right. Yeah. So let's find its radius. What is its radius? What is its radius? Okay. I think I want to work with the ratio test. Let me do ratio test. So I want to do ratio test. Yeah, let me do ratio test. We'll see. So this is a lim sup of what? Yeah, so we have an and an plus 1, right? So limit. All right, let me see what's happening. So you have 1 over n. It's probably the other way. I'll be doing it. Yeah. Okay. Okay, let me fix this so I don't get any complaints. So here it was plus 1. I think so. Anyhow, what is it? So you get n, and then you get 2 to the 2n plus 1. Actually, let me write it the whole thing. So 2 to the 2n plus 1 over n plus 1, and then 2 to the 2n over n. All right, it's quite a mouthful. So what do we get? We get n plus 1. So that guy goes to 1, so it's useless. And then you have 2 to the 2n times 2, and 2 to the 2n like that. Right. So let me see. What do I want to say? Okay, so ratio test doesn't work. Okay, so ratio test fails. So that's a good example, good. So you cannot use ratio test. So we have to use the lim sup. It's tricky. So we have n, and then 2 to the 2n, 1 over n. Again, this guy is irrelevant. And then here, I don't know what I'm doing. Am I doing this right? Oh, I know, I made a mistake. Perfect. I always make mistakes. Plus 2. Okay. All right, fine. So you get 4. So you get r is 1 over 4. Okay, everyone. So yeah, I sort of messed up the definition. I have to make my TeX index bigger. So this is like this. I thought it was 2 to the n, but no, it's 2 to the 2n. Or if you like, 4 to the n. I wish they wrote it like this. It's too confusing. All right, fine. So by Hadamard, the summation of 4 to the n, x to the n converges for all x you know, inside minus RR, inside minus 1/4, 1/4. Okay. All right. So now let's check. Is that okay with everyone? Okay. So now let's check the endpoints. R equal to plus minus R, plus minus 1/4. Okay, so let's see. At x equal to 1/4, we get 4n n 1/4 to the n, so you get 1/n. And at x equal to minus 1/4, you get 4n minus 1/4, so you get minus 1 and to the n. Hopefully you know which one converges and which one doesn't. Let's see. So the first guy is called the harmonic series. And it diverges. This guy is called the alternating series. And it converges. Just as a quick recall, what's the proof of that? This guy is bigger than, you know, n 1/x dx, you know, which is equal to, what do I want to say? No, it's already infinite. Let me call it 2n. So this is a log of n, which goes to infinity. So the tail sum, you know, is infinity. And this guy, we use the, how do you say it? We use what we talked about last time, that this guy is dominated by the last term, and it goes to 0, so tail sum converges. So sum converges. Fine. This is the tail sum. Okay with everyone? Any questions? All right. So yeah. So let me make it clear. Conclusion. The sum 4n n x to the n converges for x in, what is it, closed minus 1/4, open 1/4. So you will see this question, so make sure you understand what we're doing here. Right. So what's next? Yeah. We talked about swapping derivative and sum. Yeah, let me do the Cauchy product. So, okay, so what is the radius? We might not have time to prove it all, but you can use it of sum and product of power series. So let me just write the result, and you are free to use it, and I will try to prove as much as possible in the given time. Okay, so a proposition. Suppose summation AK xk has radius r1, and bk xk has radius r2. Then their sum, then AK plus BK has radius R less than the min R1 and R2. And what was for max? Let me remember. And same for the product. But for the product, it's a bit hard to prove, so I will do that. For the sum, I think you can see it. Has radius R less than, again, the min. Okay. Any questions, comments? If you want me to go back, just let me know. All right. So, yeah, the first one is clear. Let's prove for the product. Okay. So where am I? Right. So recall, hopefully you've seen this. If not, let me know, and we can do it after in office hours. Recall. So here we prove it for the product. Right. So recall that, that if you have a product of power series, let me change the index to not confuse you. This is equal to what is called the Cauchy product. So let me write this. N0 to infinity of Cn x to the n, where Cn goes from K0 to n, An, and then Bn minus K. Okay. So the proof of this is, how do you call it? Yeah, let me call this L. Let let n equal like K plus L. All right. Any questions? No? All right. Okay, fine. So yeah, the radius, 1 over radius is equal to lim sup of Cn 1 over n. Okay. So let me try now. So that's so we're trying to want to show that this is less than the max of 1 over R1 and 1 over R2. Okay. All right. Fine. So since R1 is the radius, no questions today. Is there really? No, we had some questions. Okay. Is the radius for summation an xn? We get that an is less than, what is it? 1 over R1 epsilon to the n for fixed epsilon. I mean, if you don't have questions here, then I don't know what to say. And for all n bigger than n epsilon. And same for but right, so we do this, but we in fact can get it for all of them. For all n bigger than 1, for some m. Really, no questions. Okay, probably nobody's here. Okay, I'll keep going for the recording at least. Okay, so we have this. Okay, so what do we have? So Cn was equal to the you know, AK Bn minus K. So like this. And then you use your bounds. So uh, 1 over R1 plus epsilon naught to the K, and 1 over R2 epsilon naught to the N minus K. Fine. So 1 over R2 to the N. And yeah, so you can show, what was my estimate? Yeah, you can get, let me write M. Yeah, you can get this. Fine, I don't care. So lim sup Cn 1 over n is less than lim sup of n squared 1 over n, n plus 1 over n, and then epsilon naught 2 n over n. These guys go to 1. And you're left with epsilon naught plus the max of 1 over Rn and 1 over R2. Okay, so we're done for today then. Oh, we have questions. Good. Is it because of alpha being the lim sup? Is it because of alpha being? Yes, exactly. So so the thing we used here, we used that we use that lim sup of an 1 over n is equal to 1 over r1. And this is lim sup, so you don't have equality. You only have inequality. So it means that for every epsilon, so for fixed epsilon naught, there exists n epsilon naught positive, so that for all n bigger than n epsilon naught, you get an 1 over n is less than 1 over r1 plus epsilon naught. And then we took powers. Is that okay, Trevor? Trevor? Yeah, okay. How did we take this guy out of, yeah, let's see. No, it doesn't. Look at it. So the summation, the sum is over k. And this guy, you know, like, just to make it more clear, how do you say it? Yeah, you know, like this guy is equal to what we wrote. Like that. So this guy is constant, constant in k. Yeah. Yeah, I'll stick around if you have questions. How did we derive Cn? Okay, good. So let's do this. So this is called the Cauchy product. So if you have AK xk times BL XL, then we claim that this is equal to Cn xn, where Cn is AK and Bn minus K to Bn. Okay, let's do this. So we start from the left-hand side. K and then L. And you have AK, BL, and then XK plus L. So that's really the key point, that you get a sum here. Okay. Then write this as follows. Set N to be K plus L. Okay, so let me write them again. K0, L0, AK, BL, and then X to the N. Okay. Where we mean N is a function of K and L. Okay. Now, well, let's rearrange this. So this is really a product. So we have a KL product where they start from 0, 0. Right. And what we do is we want to look at we want to fix we want to fix N. So let's do that. So we start from N equals 0. to infinity. And then we look at all KL that are equal to n. Right, so going from here to here, it's a bit complicated. So what we do is, so K plus L is equal to N. So I want to draw this picture correctly. So it's something like this. Okay, let me see. So K is minus L plus N. When L is 0, you get N. When K is 0, you get minus N. You get N. Okay, so you just have, so it's quite tricky. So it says KL is, KL is an element of naturals to the square, and it says split this into these level sets. So, +1 and +2. And yeah, you have and they all fall on this on these level sets, and that's what we do here. We split N2 into level sets. If anyone has a quicker proof, please let me know. But I like it because it's very geometric. I like this proof. So yeah, and then you're done. You let you know what L is. So L is N minus K. N minus K. And so indeed you get C1. Is that okay, Sanwoo? It's a tough proof. Yeah, okay. It's a very difficult proof, but I like the geometry. It's very beautiful.